This is a problem I came up with after our stairwell ball drop activity and my attempts to throw the ball back up to the third floor between trials. And in the problem, it says a student is standing on the second level, 3.5 meters above the ground, and observes the ball passing by his position with an upward velocity of 12 meters per second. The ball then reaches its peak and begins to descend when it is caught at the third floor railing located 7.5 meters above the ground. Question asks, how fast did it leave my hand, assuming my hand was at the ground level, and how long was the ball in the air in total? So let's again start with a picture. So this one's kind of needs to be broken into a couple parts, but I'm going to start with the ground, and I'm going to make sure we know that up is positive, and the ball is going to start down here. And sometimes it can be helpful to label different positions that you need with a number or a letter. I'm just going to say that this is position 1. And this ball is going to go up, and like any object, it's going to slow down, it's going to start to fall. All right, and at this position at the top, that's our railing, and here's our student who's out and catches that ball. And so that's another position there, and we'll call that position 3 because down here is another railing, and this is the observer who observes the ball passing by at this position. Call that position 2. And so these positions, we actually know what these values are. This is at 0 meters. This position is at 3.5 meters. And this position is at 7.5 meters. And we'll use those values in a little bit. And now at position 2, there's an upward velocity that this person observes the ball traveling at 12 meters per second. And I believe that's all the information we know going into the problem. So what we really want to know is, what is this initial velocity that the ball leaves my hand as it moves upwards? And from the information we know it's going to travel 3.5 meters upwards, and when it gets to position 2, it'll have 12 meters per second of velocity left. Now that's after gravity has taken away some velocity. Because remember, the acceleration due to gravity acts downward, and it's equal to negative 9.8 meters per second squared. So for every second that ball is flying, it loses 9.8 meters per second of velocity. So we know this ball must have started faster than 12 meters per second at the bottom because it lost velocity on the way up as it slowed down, but still remained at 12 meters per second at that point. And it'll continue to slow down, and at the top, the very top, we know its velocity is 0, and it appears it's going to gain some velocity as it comes down because it says it begins to descend when it is caught at the third floor level. So if I want to start with question part A, I want to know how fast it left my hand, and that would be my V initial. And what I want to do is look at the transition between position 1 and position 2. So we're going to look at our ATVX table from position 1 to position 2. And so that table will have an initial and final velocity, initial and final position. You could just as easily say V1 and V2 and X1 and X2, but our equations we've been using are initial and final. And again, final really only references the point that we care about, and that position can change along the path of an object. A is negative 9.8 meters per second squared. It's downward. Again, up is positive. We don't know the time. The initial velocity is what we're trying to find out. The final velocity, we know at position 2, it's going positive 12 meters per second. It started its initial position, we call that 0 meters, and its final position is now at 3.5 meters. So I have a bunch of variables. I'm trying to find V initial. I don't have time. However, we have a great equation that's good when we are not given time, and that's our VF squared equation, which says that VF squared is V initial squared plus 2a delta x, which is x final minus x initial. And if I look at that equation, I have V final, I have V initial, I'm sorry, I don't have V initial, but I do have A and the 2 positions. I have everything except for V initial, which means I can solve for it directly with one equation. And so I'm going to plug in what I have. V final is 12 meters per second. I'm going to square that. The initial I don't know, plus 2 times negative 9.8 times the final position, which is 3.5, minus 0. And when I start to clean that up, I get 144 on the left side equals V initial squared minus 2 times 9.8 times 3.5, which I believe is 68.6. And then it's a little algebra from there. Add 68.6 to both sides. And I get 212.6 equals V initial squared. And then we got to make sure we remember that's V initial squared, so I need to take the square root of both sides. And that's going to be V initial equals, now remember, what's tricky about this equation is because it's squared, you have to remember you actually get two answers, plus or minus 14.58 meters per second. But that doesn't mean that the answer is both. We have to look at our problem and understand what is really happening here. We know that this vector arrow for velocity initial is upward, and so I'm going to keep the positive value because that's the direction of the velocity that I have in my picture. So V initial for part A is equal to positive 14.58 meters per second. And now we're going to move on to part B. Part B asks how long the ball was in the air. Well, the ball left the ground and finished at a height of 7.5. So we really want to look at the flight of the ball from position 1 all the way to position 3. And since they're new positions, we have a new ATVX table. A equals negative 9.8 meters per second squared. Time is what we're trying to find. The initial velocity we just found is positive 14.58 meters per second. That's the velocity that it left my hand in order to travel upward. V final, careful here, it's not necessarily 0. Since it's descending as it's caught, we know it reached 0 at the very top, but then it fell a little further. So it's going to have, in this case, it looks like some kind of final velocity that's downward position. So I don't know V final, but I expect it to be a negative value based on my picture. My initial position is on the ground, and my final position is at 7.5 meters, the height of the third railing. And so I'm trying to get T. I don't have VF. So my equation that has T but doesn't have VF is my position equation, 1/2 AT squared plus V initial T plus X initial. Again, I have everything except for T. And I'm going to plug in what I have. The final position is 7.5. And that equals 1/2 times negative 9.8 T squared plus the initial velocity, 14.58 T, plus the initial position, 0. And if I clean that up, I get 0, excuse me, not 0, 7.5 equals negative 4.9 T squared plus 14.58 T. And that's a quadratic function. Now, one way to do it is to solve it with the quadratic formula. Now, before I do that, I want to show you we have a way we can do it graphically. Now, one way to think of this is graphing y equals negative 4.9. Now, they don't have t in here, so I'm going to put x squared plus 14.58 x. If I graph y equals that and set y equal to 7.5, that would be like putting another line at a height of 7.5. And so if I graph both of these lines, I'm going to hit zoom fit to get them both in the same graph. I should get a downward facing parabola. That one didn't clean up very well. Let's check my window here. So if the graph doesn't show up like you expect, let's change our window. So x is our time. We think it's going to happen in less than from 0 to 10 seconds. But my y min, well, it's not going below the ground, and it's got to go all the way up at least 7.5 meters. Let's just set it at 10, and let's graph again. There we go. That looks better. and we should get my horizontal line. There we go, that's my balcony. And so it kind of looks like my picture over here. And what I'm looking for is where that parabola intersects the line on the right, and I can do a function calc. 5 is intersect, and see if I can find my cursor here. Acting a little weird for me here. Scrolling left. There's a cursor. And I'll pick to the left of the line, hit enter, click to the right of the line, I'll hit the second curve, and then take a guess in the middle. And this actually spits out my value for the intersection at 2.31 is x, and that's going to be my time. So right there I got my value for time is 2.31, which should be my answer. That's one way to do it graphically. Now let's jump back to my equation and solve it with a little algebra. Now, if we're solving a quadratic, we want to get 0 on one side. So I get 0 equals negative 4.9 t squared plus 14.58 t minus 7.5. And again, we use our quadratic formula. And the quadratic formula, you have to identify your a term, which is always with the t squared. Your b is with the t. And your c is your constant at the end. And the quadratic formula says that t, in this case, not x, is negative b plus or minus the square root of b squared minus 4ac all over 2a. And we can plug that into our calculator. Second quit. Now, I have a program, and again, if I show you, I've actually typed in, and this program will do the work for me. So I'm going to go right to my program, type in my values, negative 4.9. My initial velocity was 14.58. That's my e term. And negative 7.5 is the height. And I get my 2 times. Again, I get 2 of them, and they're both positive in this case. 0.66 and 2.31. Now, we already saw graphically that where it lands is 2.31, but what's that first one? Well, as this ball moves up, it actually passes through that height twice. It passes on the way up, 2.66 seconds later, and it passes on the way down, 2.31 seconds later. And the problem says that it is descending when it is caught, and so we want the time that occurred when it was coming down. So the answer to this problem is going to be 2.31 seconds when the ball is coming down. And the traditional way to solve this by graphing, instead of drawing 2 lines, is I can delete this out and just set it equal to 0 and subtract 7.5. And that just shifts my graph down. And when I graph again, it'll be a little lower. And what I'm looking for now are my x-intercepts, my zeros. So if I go to 2, I can scroll left and find my values. I know my time should be 2.3. Struggling to find my cursor here. There it is. My left bound, hit enter. I'm going to scroll past that x-axis, hit enter, and then take a guess in between. And again, it's going to hit my 0 and y is 0 at 2.31. So again, just to show you another way to graph, again, my scale is not great. I probably would be helpful to change my window. We go from -5 to +5 in the y, and that way you can really see those values. Again, you should get comfortable moving the window around on your graph. Hopefully this helps, showed you a bunch of different ways to solve a quadratic and solve a tricky problem that you have to break down into pieces. And there's all your work.